Okay, guys, welcome. Today we're going to talk about the Euclidean algorithm as well as greatest common divisors. So first we're going to start with the greatest common divisor. The greatest common divisor of two positive integers a and b is the largest positive integer that is a divisor of both a and b. And we denote this by GCD parenthesis AB. Okay, so some examples are that the GCD of 1 and 6 is, of course, 1 because 1 is the biggest number that divides both of them. Then the GCD of 2 and 6 is 2, 3 and 6 is 3, 4 and 6 is 2, GCD of 5 and 6 is 1, and of 6 and 6, of course, is 6. Now we say that A and B are relatively prime if their greatest common divisor is 1, right? So for example, 5 and 6 would be relatively prime because their greatest common divisor is 1. Now we're also going to define the greatest common divisor of a and 0 to always be a for any a that's bigger than or equal to 0. Okay, now the least common multiple of two integers a and b is the least or the smallest positive integer that is a multiple of both integers. And we denote that by LCM of a, b. Right, so for 1 and 6, of course, that's 6. For 2 and 6, that's 6. For 3 and 6, that's 6. Now for 4 and 6, right, I can't multiply 4 by something and get 6, so we need to do better than that, right? So it turns out that the next one that we can do is 12, right? And then 5 and 6 will, of course, give us 30, and 6 and 6 will give us 6. Now, the way that we can find the GCD of two positive integers is to find the prime factorizations of each number, look at the common prime factors, and then raise each to the smaller of the two exponents, and then find the products of these. Right, so for example, let's find the GCD of 954, given that 900 is 2 squared times 3 squared times 5 squared, and 54 is 2 times 3 to the third. Okay, so now what we do, now that we have the prime factorizations, we look at the common prime factors, right? So we have 2's in both, and we have 3's in both. Okay, now once we do that, we raise each to the smaller of the two exponents. So it looks like the smaller of my exponent for 2 is just 2 to the first, or 2. And my smallest power of 3 is 3 squared, right? And then if I multiply these together, I'm going to get 2 times 3 squared, or 2 times 9, which is 18. And it turns out that 18 is the largest number that will divide both of these. Okay, now the difficulty with this is that sometimes it's hard to find the prime factorization of large integers. And of course, we're going to discuss a more efficient method, which of course is the Euclidean algorithm. All right, but before we do that, we're going to do a couple of examples that's going to allow us to use the Euclidean algorithm, with reason. Okay, so now for part A, we want to show that for any positive integers a and b, if we have a dividing b, then that means that the GCD of a and b is equal to a. Well, if a divides b, that means that a times k is equal to b, right? And that means that I can plug in an a times k for b, but now this is the biggest number that I can take out of a is a, and I might be able to take something like a times 2 or a times 5 out of this ak term, but the thing that's limiting me is the a in the first coordinate here. So my GCD, of course, is going to be a. Okay, and that's the idea. Now for part B, we want to prove that the GCD of a comma b is the same as the GCD of a comma b minus a. Okay, now there's a couple different ways that you could do this. One way to do it is let D equal the GCD of A and B, right? Now, if D is the GCD of A and B, that means that D divides A and D divides B, right? And we showed before that if D divides two numbers, then it divides their difference, right? Or D divides B minus A, right? Now, of course, what this means is that if D divides B minus A, that means that D is less than or equal to the GCD of B minus A. Sorry, A comma B minus A. Right, because the greatest common divisor might be bigger than B minus A. Now, if we do this another way, we could also do, to get the reverse inclusion, we need to do something like this. Now, it's kind of silly, but we're sort of just going to change the roles of D and the GCD, right? So now we would just say that the GCD of A and B divides A, and the GCD of A and B, of course, divides B, right? So this tells us that the GCD of A and B divides B minus A. And of course, if we have D then this is less than or equal to D because D also divides A and B as well. So now these two things together prove that the GCD of A and B, in fact, is D. Okay, so then that means that the GCD of A and B minus A is the same. Right, and I guess actually I should make it this way. Let's be a little bit more precise here, I guess. Okay, so then we could also say that if D star is the GCD of A and B minus A, then that means that D star divides A and D star divides B minus A. So then we get that D star divides their sum and D star divides B, right? So then that gives me that D star is less than or equal to the GCD of A and B, right? So then that's the idea. That's how you could sort of formalize it there. Okay, now how can you find the least common multiple of two integers if you know their prime factorizations? Well, it's going to be similar, except first, right, find the prime factorizations. Okay, I realized I forgot to do part C, so I paused it and went back. So part C basically says that R is the remainder of when we divide B divided by A, okay? Now we want to prove that the GCD of A and B is the same as the GCD of A and R. Now, again, remember that we proved B, which is that the GCD of A and B is equal to the GCD of B minus A, right? Now, by this argument, A and B minus A. Now, by this argument, we could apply this again and get that this is the GCD of A and B minus 2A. right? Or GCD of A and B plus A times K for any integer K. Right, and let me put minus just so that it matches sort of what we had. AK, right, although K could be any integer, and if K was negative, could make that positive. Now, since we have that R is equal to B minus AQ, we can now substitute that into here and we're done, right? Then we get that the GCD of A comma B is the same as the GCD of A and R. Okay, so now back to the example that we started. How can you find the LCM of two integers if you know their prime factorizations? So of course you would want to find the prime factorizations, and now you find the highest power of all prime factors for both integers. And then of course, the last thing would be to find their product, and then that's your LCM. All right, and we'll do an example that involves that. So the example that we're going to do is we're going to prove that for any two integers A and B, let GCD, we want to show that the GCD of A times A and B times the LCM of A and B is A times B. Let's just write down what the prime factorizations would be. So we'll say that A is P1 to the K1, P2 to the K2, all the way to Pn to the Kn. And we'll say that B is Q1 to the P1, not P1, L1, let's say, Q2 to the L2, and so on, Qn to the Lm, because these could be different. Okay, now hopefully it's clear that if you multiply these together, you're going to get A times B, of course, right? But now let's also pick out, let's say that, suppose that, let's say that R, let's say R1 to the, R1 to the J1, R2 to the J2, I'm going to run out of letters here. Let's say RD to the JD are the primes common to both. Right, so in other words, this is the GCD of A and B. Okay, well now what would the LCM of these two be? Well, the LCM would be whatever's sort of left over, right? Because the LCM takes the largest power. Power of any primes. Right, so for example, we might take Q1, L1, then P2, K2, and so on and so forth, and the last one might be Pn, Kn or something, right? But now when I multiply these together, I'm getting everything that I missed in the GCD part, right? So you can really sort of, let's maybe just look at an example. Let's look at an example. Let's say that A is equal to 7 and B is equal to 21, just to make this easy. Well, the GCD of 7 and 21, of course, is equal to just 7. And the LCM of 7 and 21, of course, is 21. And if you multiply A times B, that's just 7 times 21, right? And of course, you would see that those products would be equal. Now, of course, this is an example where you have one being a multiple of the other, so it's maybe a little bit easier to see, but you can try it on your own for some other numbers and see that this will work out every time. Right? It's sort of hard to explain this idea without it getting too messy. So maybe it's better to just do a couple of examples and sort of see it that way. Okay, but now anyway, we can finally talk about the Euclidean algorithm. Right? So suppose we are given two positive integers a and b, and we want to find their GCD. Right? Now, if a is greater than b, we're first going to interchange a and b, right? Because we know that the GCD of a comma b is the same as the GCD of b comma a. Right? So we're going to switch them. Now, if a is greater than 0, you're going to divide b by a to get a remainder, and you're going to replace b by that remainder, and then go back to step 1. All right, and you're going to keep doing this until a is equal to 0, and then once you do that, whatever is left is your GCD. All right, so let's look at an example. Okay, and we want to find the GCD of 318. So first of all, my a is bigger than my b, so I'm going to switch these two. So I'm going to put 18 in the first slot and 300 in the second slot. Now, if I divide 300 by 18, I get 16, but I have a remainder of 12, right? And that's what's now going to become this part right here. And again, we're allowed to do this because the GCD of a and b is equal to the GCD of a and r if b is equal to aq plus r, right? That's what we did in the last problem. And now we just repeat, right? So now we switch 12 and 18 because 12 is smaller. And then, of course, 12 goes into 18 one time with 6 left over. So we're going to replace the 18 with the 6 there. And then we'll switch 6 and 12 again. And then finally, 6 goes into 12 two times, and there is no remainder. So now we get the 0 that we want. So we get that the GCD, of course, is 6. Okay, so let's do another example. Okay, so the first step, I want to switch my a and b. So now this is GCD of 100 and 101. Well, how many times does 100 go into 101? Well, it goes in one time with 1 left over. And of course, since that 1 is the remainder, this is now GCD of 100, comma 1. Right? And now we switch our 1 and our 100 again. How many times does 1 go into 100? At this point, you can probably see what the answer is going to be. But we have 1 and then 100 times 1 plus 0. So we get GCD of 1 and 0. And this, of course, is just going to be 1. All right, so that's our GCD of 101 and 100. Okay, let's do another one. So now first, let's switch 89 and 55. Of course, the switching of these two elements, of course, is just, it's just sort of for show. You don't have to do the switching every time. This is just what the textbook recommends. So just to sort of be, keep everything consistent, I'll do it that way as well. Okay, but we want to write 89 as a multiple of 55. So this is going to be 55 times 1. And let's see, to get to 89, I guess we need to add a 34. Okay, so now this is the same as the GCD of, now I'll put 34 here and then 55. And then this is GCD of 34, and then I'm going to have 34 times 1, and it looks like I need plus 21. So this is the GCD of 21 and 34. So I'm going to get GCD of 21, and then 21 times 1 plus 13, which is GCD of 21 and 13, which is the GCD of 13 and 21. So then 21, I can write as 13 times 1 plus 8. So this is the GCD of 13 and 8, or 8 and 13. So this is the GCD of 8, and then I can write 13 as 8 times 1 plus 5. And I can write that as the GCD of 8 and 5. So this is the GCD of 5, and then 5 times 1 plus 3. So GCD of 3 and 5, which is the GCD, so along with 3, and 3 times 1 plus 2, which is the GCD of 3 and 2, which is the GCD of 2, comma 2 times 1 plus 1, which is the GCD of 2 and 1. So finally, we get that this is 1, comma 1 times 2 plus 0. So we get the GCD of 1 and 0, which finally we can say is 1. Okay. Now, I wanted to do this last example just to show that even though it seems like this is going to go on forever, it of course never will, right? Why doesn't this last forever? Well, you have that your numbers are decreasing always, but you always have this fact that they're always positive, right? So we know that eventually this is going to end despite some problems like this last one that we did maybe taking a long time. Okay. Now, during the use of the Euclidean algorithm, the product of the two current numbers drops by a factor of at least 2 in each iteration, right? And the proof is the following. We're going to consider the step where the GCD of A comma B becomes a GCD of R comma A, right? So what happens there is that since R is less than A, we know that if we were to and we know that A plus R is less than or equal to B, we know that if we were to add R to both sides of this one, right, we get that 2R on this side is less than A plus R, but A plus R is less than or equal to B. So we get that AR is less than 1/2 of A times B, right? So we can see that we're going to decrease by a factor of 2. At least 2 for each iteration. Okay. Now the next theorem is that the number of steps of the Euclidean algorithm applied to two positive integers A and B is at most log base 2 of A plus log base 2 of B. Okay. So the proof of this is to suppose we're applying the Euclidean algorithm to two numbers A and B, and we make k steps. Now by the previous lemma, after k steps, the product of the two current numbers will be at most AB over 2 to the k, right? And again, of course, because you're dropping by a factor of 2 each time, so for k steps, it's 2 to the k. Now, since this is a positive integer and it has to be at least 1, right, we know that AB over 2 to the k is greater than or equal to 1. So then multiply both sides by 2 to the k and we get this. Okay, and then of course, if we use logarithms, you'll find that k is less than or equal to the log base 2 of A times B, which using your log rules, you can separate into that sum there. Okay, now another interesting fact is the following. Now we found that the GCD of 318 eventually was 6, right? Now, of course, where did this 12 come from? 12 was the remainder of 300 divided by 18. So if you wanted to, we could write 300 is equal to 16 times 18 plus 12. And rearranging this, we could say that 12 is equal to 300 minus 16 times 18. Right? And then a similar thing for 18. We know that 18 came from 12 times 1 plus 6. And then we could write for our 12, our expression that we found for 12, And then once we combine our like terms, right, we have a 300 that we're subtracting. And then we have minus 16 18s. And then once I subtract this 18 over, I'm going to pick up one more, right? And that's where we get, and I guess really what I'm doing is I'm bringing this stuff over. Right, so I'm getting 17 18s minus 300 is equal to 6. And it turns out that all the numbers that you produce by the Euclidean algorithm can be written this way. And we'll do a little bit more of this in the next chapter. But this gives us an important theorem that if we let D be the GCD of A and B, we can write this GCD in the form A times N plus B times N, where these two numbers are integers. And this is going to be what we look at next week. This is an example of a Diophantine equation. Okay, now let's look at the proof of this. So we're going to suppose that this holds for two consecutive numbers that we found. We'll say that A prime is AN plus BN, and B prime is AK plus BL, where M, N, K, and L are all integers. Well, then in the next step, once I subtract Q times B prime over, I'm taking this, which is my A prime, minus Q times this, which is my B prime, and then we can refactor it as A times some other integer plus B times some other integer. And of course, that completes the proof. Okay, so that concludes this video on the Euclidean algorithm. I hope you enjoyed, and I'll see you next time.